Hello. In this project, wetland loss along the Gulf Coast of Texas due to sea level rise will be examined thoroughly. This will be done by comparing relevant data, studying historical trends of sea level rise and wetland loss, and projecting relative sea level rise for the next 50 years to project future loss. Wetlands are incredibly valuable, not just for biodiversity, but for a number of other beneficial services, commonly referred to as environmental services. These services include, but are not limited to, recreation, carbon sequestration, water treatment, flood protection, and biomass production. The most critical service examined today is flood protection, as wetlands provide a buffer that protects coastal communities. Wetlands have existed for millennia by remaining adaptive and adjusting to limiting factors. Historically, sea level rise has encouraged accretion of soil, which has likewise lifted affected wetlands to higher elevations, allowing them to maintain their area despite changes in sea level. However, if sea level increases too quickly, erosion occurs much faster than accretion. Additionally, increasing development, sometimes referred to as urban sprawl, limits the potential for wetlands to move upland. The increasing pressure on both sides of a wetland has been coined the coastal squeeze. These factors, as well as others related to climate change and urbanization, have reduced coastal wetlands by a third of their area. It's important to map these factors alongside wetland loss to further understand the spatial relationship. There have been many studies examining wetland losses, including this study conducted by Texas A&M University professors that examines the loss of various wetlands and what they've been displaced by. Note that salt marsh transitions upland as tidal flats take over the existing areas. This graph represents annual sea level measured in Galveston and maintained by the Permanent Service for Mean Sea Level, or PSMSL. When plotted with a line of best fit, the gauge demonstrates a rise of 6.6 millimeters per year. The average rise across all active Texas stations for the PSMSL is 7.7 millimeters per year. This was confirmed by examining NOAA gauges, which show very similar values. Unfortunately, linear rise is not a reality. Multiple studies and organizations predict a much faster rate over time, varying from 0.59 meters to 3.4 meters by 2100. This project will explore what area of wetlands along the Texas Gulf Coast are at risk of being displaced due to sea level rise over the next 50 years. 50 years was chosen as the standard lifespan for most protective engineering developments that could be used to protect coastal regions. The questions that we will be examining are: which data source is best for wetland classification? Is the DEM, or Digital Elevation Model, provided by the United States Geological Survey sufficient for this study compared to the LiDAR analysis done by NOAA? What is the total area inundated by sea level rise alone in 50 years? Of that area, what percent of it is wetlands? What percent of wetlands in the study area are at risk? And how do the boundaries of development limit the movement of wetlands? All maps shown in this presentation will be according to the North American datum of 1983 in the Universal Transverse Mercator Projection of Zone 14N. This projection is a cylindrical projection and maintains local shapes and angles. While 3 zones go through Texas in the Universal Transverse Mercator Projection, Zone 14 was selected as it covers the southern Gulf Coast. Sea level rise is assumed to be linear despite the predictions that it may be much closer to a quadratic increase. Relative sea level rise is used to examine the difference in inundation along the coast. Unless otherwise stated, meters are used in all maps. To begin this project, the data sources had to be compared to determine which one was the most suitable for this project. There was 2 primary sources of wetland data used: the National Wetlands Inventory and the National Land Cover Database. Both included a 30-meter resolution and examined more than one wetland classification. They are compared here. Of the 2, the National Land Cover Database was chosen. It was chosen because other land cover information, such as development, can be examined on a similar scale and with similar parameters. And the raster for the National Land Cover Database produced less errors when working than the National Wetland Inventory data. The land cover data set does have less wetland classes than the National Wetland Inventory, but this did allow for a smaller file size to work with, which became a necessity further in this project to examine the entirety of the Texas Gulf Coast. Two different digital elevation models, or DEMs, were examined. One was from the National Oceanic and Atmospheric Administration, or NOAA, and constructed from LIDAR, or light detection and ranging. This set had a resolution of 3 meters. In contrast, there is a DEM from the United States Geological Survey, which had a resolution of 30 meters. They are shown here. The data set from NOAA, the LIDAR data set, is shown on the top, and the data set from USGS is shown on the bottom. While it is true that NOAA's data has 10 times the resolution, which is valuable when looking at areas with low slope-like wetlands, it represents a much smaller area along the coast, and it has multiple invalid points, as shown on the far right upper image. All of the points that are extremely dark were invalid points, so they could not be used. The data from USGS is more continuous and has no invalid points, so it was ultimately chosen to work with for this project. It should be noted that this choice, as the USGS project and DEM is less accurate with a 30-meter resolution, decreases the precision of this project. The National Land Cover Database has classification from 2001 to 2019. So first, it was critical to see what changes have already occurred compared to the sea level rise over that time period. This map shows the land use from 2001 and the change in land use from 2001 to 2019, using classifications from the National Land Cover Database. Wetlands, particularly emergent herbaceous wetlands, are centered along the coast. Some water change can already be seen as well, particularly in this lower area here. This map shows the same data, but it's zoomed in on the land between Sabine Pass and Galveston. It becomes more apparent that the open water gain is primarily over wetlands. Urban expansion can also be seen increasing along the edges of existing water bodies. These spots here in the teal color are the water change, which you can see over the existing emergent herbaceous wetlands. And you can see developing land occurring here along Matagorda Bay and up here near Sabine Pass. This is the same data, but it's been zoomed in on the land between Rockport and Corpus Christi. Interestingly, we can see some water change inland in this region affecting more than coastal areas, particularly around Lake Corpus Christi. This chart shows the land use in 2001 of this region in Texas. Woody wetlands make up 10% of the land area, and emergent herbaceous wetlands make up 4% of the land area. In contrast, this chart shows land use in 2019. Woody wetlands have dropped to only 2% of the region's area, and emergent herbaceous wetlands have dropped to 1%. Interestingly, when only looking at these two pie charts, the loss does not appear to be related to any development or conversion to open water, but actually to agricultural uplands. The sea level rise from 2001 to 2019 was found and interpolated across the area. It varied from 0.12 meters to 0.24 meters across the coastline, with the largest relative rise along Sabine Pass and Corpus Christi. The change in wetlands, water, and urban development are shown overlaid. So you can see an increase in urban change around major developing cities like Houston, as well as water change between Corpus Christi and Port Isabel, as well as in some areas that we will zoom into. As we examine the region between Galveston and Sabine Pass, it becomes apparent the wetlands have changed between classes. Additionally, some inundated areas are shown along larger bodies of water like Matagorda Bay. So changing wetlands between classes may imply that wetlands are changing from a more saline wetland to a freshwater wetland, or vice versa. As saline water creeps in due to sea level rise, we may see freshwater wetlands converting or woody wetlands converting to a more herbaceous salt marsh grassland wetland. Examining the region between Rockport and Corpus Christi, we can see a lot more development. Existing wetlands were already pretty scarce in this area, but we can see increased inundation upriver, especially around Lake Corpus Christi. When we zoom into Lake Corpus Christi, the Identify tool can describe multiple layer values, including ones that are not shown in this image. Note how this area that's been converted to open water converted from the emergent herbaceous wetland. The sea level in this area only increased by 0.022 meters, according to the PSMSL. Yet it converted all of this land surrounding this body of water into open water. This trend is reflected across the entire map. With the linear progression of sea level rise predicted from the PSMSL, the areas in the DEM at risk can be determined. As we see here, Sabine Pass has the largest relative sea level trend and Rockport has the lowest. This map here was formed using interpolation, which was converted into meters and multiplied by 50 to represent a 50-year trend. This map shows what the Texas coastline may look like in 50 years under the current trend of sea level rise. Note that the PSMSL stations are placed along the existing coastline. Sabine Pass, which experiences the largest relative sea level rise and has a high number of wetlands, also experiences the greatest loss of area. Current wetlands and development are overlaid in this map. This map more clearly shows the existing coastline. As you can see, it is defined by existing wetlands. The majority of wetlands existing are shown as underwater using this predicted rise. Additionally, the development borders the upland edge of all of the wetlands, which will limit upland migration and contribute to the coastal squeeze phenomenon. This flowchart illustrates the geoprocessing that was done to arrive at this final map shown previously. Note the use of the IDW tool to interpolate all of the PSMSL data, as well as the raster calculator tool used to combine the different rasters. It was critical to maintain the same area and resolution between data for these steps. Finally, the intercept tool was used to find the affected areas. Now we return to the initial research questions. These two were covered a bit earlier. The map to the right shows the USGS DEM, and the green raster overlay is the wetlands from the National Land Cover Database. So as we discussed, which data source is best for wetland classification? While the National Wetland Inventory is in fact more detailed, it does overlap with development areas from the National Land Cover Database, and it's too large to work with over these large areas like the entirety of the Texas coastline, compared to the National Land Class Database. Is the DEM provided by USGS sufficient for this study compared to the LiDAR analysis done by NOAA? Obviously, when looking at any detailed analysis, particularly when looking at low slopes, 30-meter resolution is not ideal, and it is recommended to find a resolution comparable to the NOAA DEM without errors. However, that DEM in particular was shown impractical for the large study due to the file size. The map on the left shows the future inundated coastline overlaid on the present USGS DEM, so you can compare how the coastline will change. The question that we are looking at was, what is the total area inundated by sea level rise alone in 50 years? So of the area studied, about 1.9 million acres were inundated. This was after removing existing bodies of water post-processing. So after removing existing lakes, this represents 38% of the study area that will go underwater under this estimate. The map to the right shows the previous map, but we've overlaid the affected wetlands. Of the land area that's inundated, what percent of it is wetlands? We did processing, and according to the pixel calculations, about 8% of the inundated area is wetlands. This map shows the 2019 wetlands in this study in green. So you can see all of the wetlands that were in the study. And in red, the affected wetlands, the ones that will be affected by the 50-year rise, have been overlaid. So what percent of wetlands in this study area were at risk? Of these wetland areas, about 26% are at risk from inundation. Finally, this map shows the future coastline of Texas, the wetlands at risk in green, and the developed areas across the study area in pink. How did the boundaries of development limit movement of wetlands? Development provides a hard inland boundary, which can prevent any movement inland from wetlands. It becomes very apparent looking at this map how the wetlands can really struggle to move inland and upland as the sea level continues to rise. And it becomes incredibly apparent how important the spatial relationship is between development and wetlands. I'd like to acknowledge that this project was done for the Graduate Introduction to GIS course BAEN 651-699. The tools used were primarily by Esri, including ArcCatalog and ArcMap, but Microsoft Excel and Microsoft PowerPoint were also utilized. Data was from the National Oceanic and Atmospheric Administration, the National Land Cover Database, the Permanent Service for Mean Sea Level Rise, the United States Geologic Survey, and the United States Fish and Wildlife Service. All information used as the foundation for this project was obtained from these sources, which are cited within the presentation appropriately. All of the data utilized is cited here appropriately. I used a digital elevation model from NOAA, as well as some confirming sea level rise data. I used data from the PSMSL for the sea level rise gauge data used to form the interpolation raster. The citation below that describes the creation of that data set. I used DEMs from USGS as well as their national land cover information. I used the National Wetland Inventory created by the US Fish and Wildlife Service. Thank you so much for watching. If you have any questions, I can be reached at mehumphrey@tamu.edu. I enjoyed this class tremendously and look forward to finding new ways to use GIS in my career and education.